Today we are going to talk about dynamic source routing. So we were in the middle of ad hoc networks and we talked about one method of routing, and now we're going to talk about the second method, and there's one more. So there are total 3 methods that we'll talk about. The second one is DSR, dynamic source routing. Alright, so basically source route means that the source puts in the IP packet a list of routers where the packet should go. And that's how it finds the path to the destination. It goes to the first router in the list, then goes to the second router on the list, and third router on the list. And the route can be either strict or loose. There's a bit in the packet IP header which says whether the route is strict or loose. If it is a strict route, then when it goes from router X to router X plus 1 or router N to router N plus 1, if router N plus 1 is not directly connected, then the packet is dropped. Okay? A strict route means you cannot send it to some other router and let that router send it to N plus 1. So every router has to send it to the next router as indicated. If not, then the packet is dropped and the source is informed. So that, and loose source route means it doesn't matter how the packet goes from router N to router N plus 1, it just gets there. Okay? So that's approximate source route. So routing database, so basically each node keeps a routing database which is a complete route to resend destination. So all the destinations that it was sent, it keeps a list, and if some destination is on the list, then no problem, you just use that list, use that source route. Otherwise you send route request to all neighbors. So now this is a reactive scheme in the sense that it doesn't really work anything, it doesn't do anything before the route is required. Suppose there is no activity whole day, then no route may be present and it doesn't matter really because there is no traffic. But when the packet has to be sent and the route is not available in the table, then a route request is sent to all the neighbors. Does anybody know the route, for example, to node number 5? So now each neighbor adds itself to the route request and sends it to other neighbors. So if they don't know, then they send it to their neighbors and say, do you know the route to request to node number 5? Only on the first receipt. If they receive the same thing again, they obviously don't send it again. So this is kind of flooding which is done. If a node knows the route, it appends the rest of the route and returns the route reply. Now it is quite possible that somebody along the path knows the route to the node that you want. So it will put that route and the string that has been made so far and sends it back in the reverse direction. So route reply comes back in the reverse direction, and then the source knows that, makes a record of it, and then he uses it from that point on. If a transmission link fails, then the link error is sent to the source and all routes with that link are truncated. So for example, if there was a route and it was using link number 9, or node number 9 to 10, and that link was failed. So basically node 9 will say, I no longer have the link to 10, and will come back to the source, and source will remove all its routes that use that link between 9 and 10. Alright? Disadvantage of this scheme is that it is good if the traffic is very light, and it is good if mobility is light. Light mobility means that people are not moving that much because you're going to remember the route, and if they move very often, then the route will not be any good. So this is a method which is specified in RFC 4728. So this is a change from your handout. In your handout, it says a draft which has changed to RFC now, 4728. And the new RFC actually is in the last page of your new handout today. In the new handout last page, I have put the list of new RFCs. Actually, that page you can take off and attach to this handout, because that whole page, last page of the next handout, belongs to ad hoc routing. How do you find a source route? Yeah, suppose you don't have somebody on the list, then what do you do? So you flood a request, and whoever has the route sends it back. So now this is quite a big overhead in that case, right? But it applies to all the 3 schemes, because you see what happens is, regardless of how you do it, whether even in the current internet, all the connectivity has to go to all the routers, right? So either you have a choice of flooding it in two ways. Either you flood your little connectivity to about your neighbors to the whole world, or, and that is called link state routing, or you tell about your view of the world to your neighbors. That is called distance vector. In the distance vector, you tell just your neighbors, 5 people, that my route to 1, 2, 3, 4, 5, 7, 18, 2000 is such and such. Right? So you can send big tables to a small number of neighbors, or you send a small table everybody in the world. Yeah. So basically, what you're saying is, first of all, there is no central node. So I mean, but you could elect a leader temporarily. Basically, that might become a bottleneck, right? If all the traffic goes through a single place, this is a wireless thing, right? So there is no centralized thing, but so all the 3 schemes that we're going to talk about are distributed in that sense. They don't just assume that there is one node which knows everything. All right. So here is an example for DSR. Now, this will clarify much better. So 1 wants to send a packet to 10. It doesn't know that. So what it does is it looks at it sends to its 3 neighbors, and 3 neighbors are 2, 3, and 4. So it says 2, do you know route to 10? 3, do you know route to 10? 4, do you know route to 10? They don't know. So 2 sends it to 7 and 5. Says to 7, do you know route to 10? And 5, it says, do you know route to 10? And similarly, 3 sends it to 5 also, and 4 sends it to 6. But it turns out actually in this example that node 3 does have a route to 10. It knows that the route to 10 is 3, 5, 9, 10. And 4 has a route and it knows that it is 4, 6, 8, 10. And so both of them respond back to 1 saying that, okay, I know the route for you is now, basically you can add 1 to me. And so it will be 1, 3, 5, 7, 9, 10, and 1, 4, 6, 8, 10, 8, 9, and 10. And node 1 in this case would probably select the route through 3 because that has shorter number of hops, smaller number of hops, right? So it can keep 3 and then it can use 4 as a backup in case something goes wrong. I can just forget 4. First of all, nobody sends anything unless asked for. So 5, if something breaks between 5 and 9, or if something gets connected between 5 and 9, nobody will tell anybody, right? This is a reactive scheme, means only when somebody asks, you tell. All right. Second thing is that it was started to be flooding, but really it didn't really flood the whole network because 3 and 4 know the answer already, so they don't send it anymore. 2 did send it to 5 and 7, right? And then 5 might send it to 9, and 7 might send it to 9, and so on and so forth. So that part of the message might get flooded. But at least the 3 and 4 got stopped right there. So it is quite possible, though, on the wired network and as well as here, that you could have multiple routers on a single Ethernet. So when you send the message, it might reach them simultaneously if you did it right, but generally, no, I mean, I don't understand. So there is a link between 5 and 7 will send it to 5. And then basically what will happen is 5 has already gotten 1 from 2 before, so it will just ignore that message. Anytime you get a duplicate request, you just save it. I mean, basically you save all your requests for some time and you look into the cache. Have I heard this before? If yes, then you drop it. Don't do anything on that one. If it is new one, then you worry about whether I have the answer or whether I can send it to somebody. Well, I mean, other responses may come back later. So for example, when 2 goes to 5 and 7, 5 may respond, 7 may respond, but those would be, much too late and may or may not overwrite. See, they may overwrite if they are same length. So, well, it has to send it. So basically right now, whichever it comes first is going to send the packet, right? And then the later answers will come, they may overwrite the route. So for example, if 3's answer comes first, it is going to send via 3, or if let's say the answer comes from 4, it will send via 4 that packet and route that route in this table. But later on, a new route comes in from 3, which is better. It will write the 3 into this table. This is not cast in concrete. You could use simply hop count as a weight. but you could use something else. You could assign some other weight to each link. I mean, the scheme works exactly as before. I mean, if you say, well, this link is long, this link is short, this link is low bandwidth, this link is high bandwidth, this is an 11 link, this is a WiMAX link, this is a free link, this is a costly link. So all those things can be added as a weight. Yeah, hop-based scheme is just a simplification of weighted hops scheme, weighted link schemes, right? Every link can have a weight, and you just minimize the sum of those weights. Each link has a cost, you just minimize the sum of the cost, right? But the cost is just 1, we call it hop-based. Alright, the next and the last scheme is AODV. And AODV stands for ad hoc, on-demand, distance vector routing. So it is already giving up, in the name itself, it is giving you a lot of information. First of all, it says it is for the ad hoc networks. Second word says this is on-demand. On-demand means, is it reactive or proactive? Reactive, right? Because it is just responding on demand. Distance vector says that this is not a link state routing. If you remember, the distance vector means what? Distance vector means you tell about the whole world to all your neighbors, right? And the link state means you tell about the, so basically, so each node has a routing interval entry which says whatever destination, what is the route. Basically, this is a list of nodes. Then there is sequence number assigned to each route. So we say this is my third entry, this is my fourth entry, this is my fifth entry, and then there is a timestamp, which is actually, sequence number is like a timestamp, actually there is no explicit timestamp. So sequence number acts like a timestamp. If you have your entry number 3 and somebody says that here is the answer for entry number 4, then you just update that, you know that 4 is later than 3, is more up to date. So each source keeps a broadcast ID counter, and then also keeps a broadcast ID that this is my 15th request or 1500th request. So this is global across. This broadcast ID is basically for each source one number, whereas the sequence number is number for each route or each destination. So for each destination there is a sequence number. So you might have sequence number 3 for destination 1 and sequence number 4 for destination 2 or sequence number 2 for destination 3 and so on. Alright, where broadcast ID is simply sequence number. So it is simply a number that increases every time you send an ID, send a broadcast. So how do you do path request? Path discovery, basically you flood a route request to all your neighbors, and the neighbors broadcast it to their neighbors. Each request has the source address, source broadcast ID, destination, sources sequence number for the destination. So you say, well, I have right now the route number 3 for node 10, but does anybody have anything later than that? So intermediate nodes look at that number, and if they have a better route or a later route, then that means a higher sequence number, then they will say, okay, yeah, I have number 4. Intermediate node record the route from which the first copy was received and the reverse path. So basically, when they receive a request, they know the request came from node number 3, so they know that this is how the response should go back. And so that's how they make the reverse path, is by just remembering where the first request came from. So that's how they know the reverse path to the source. Route reply comes back on the reverse path, and each intermediate node along the way, even though they didn't ask for it, they update their table with that new number. So if you got the request number 4, you update your table to number 4. Old entries are timed out. So some entries that have not been used, they are just put out of the cache, lifetime expiry. And it supports only symmetric links. That means the cost of both going down and up is same, and therefore the reverse path is also optimal path. Otherwise you will have to find the optimal reverse path, which may be different than the forward path. If a source node moves, it should reinitiate RRQ. So basically the source remembers all the paths when it is in one location, but if it moves, then all the paths are gone, and for every node it will have to find a new path. If the intermediate nodes move, all upstream nodes broadcast a link failure to their upstream neighbor until source node is reached. So whenever an intermediate node moves and some link goes down, then people inform this source that the link has gone down. Disadvantage: intermediate nodes may send more up-to-date but still stale routes. What that means is that you have route number 3 and you ask somebody, do you have a newer route? And somebody says, yeah, I have route number 4. But they're not telling you that your route number 3 was 2 days old and my route number 4 is just 2 days and 1 hour less old. So, I mean, see, increasing number doesn't really mean that it is today's answer. It could be a very old answer. It is later than what you had, but it may not be the latest.
In that case, why don't they use timestamp instead?
Yeah, no, they don't use, even if you use, yeah, if you could use timestamp, but the thing is, basically, the way you protect this is by having a flush where basically you just don't remember any information which is more than 1 hour old or 2 hour old. So that way, when you get an answer which you know that this is pretty decent, right? And so you have that guarantee. So this is described in 3561. Here is an example. Again, the same network. We are going from 1 to 10, and we send the request to 2, 3, and 4, and we say that my number is 3. Okay? Sequence number is 3. So node 2 sends RRQ to 5 and 7. So node 2 doesn't have anything, it sends 5 and 7. 3, on the other hand, has sequence number 1. 3, on the other hand, has sequence number 1. So it forwards it to, basically, 1 is less than 3. Remember, this is the key point. That 1 is less than 3. So it cannot answer. It forwards the request to 5. And then comes node 4, which has sequence number 4, and it right away sends the response back to 1. And therefore, the node 1 then chooses 4, 6, 8, 9, 10 as the path, and number 4. Now, it is quite possible that the 5 and 7 may get a newer answer. That may be a better answer. All right, that brings to the end of this ad hoc lecture. And as we said, ad hoc means no infrastructure, and that way it is very resilient. Resilient means that it is susceptible to, basically it survives the failures. If something fails, it still works. It is useful in military and emergency situation when the infrastructure may have failed. It also results in multi-hop communication over the wireless. Now you have 2 kinds, proactive, reactive, and hybrid. 3 kinds actually. Hybrid is a combination of reactive and proactive. So AODV is reactive, distance vector based. DSR is reactive, also distance vector based. In both cases you keep the route. And OLSR is proactive, link state based. Okay? So now all this lecture, actually the best book is Murthy and Manoj. So this book is actually in the library. I would recommend that you read it. And then there are 4 RFCs which talk about the protocols that we talked about. The 3 RFCs are on the 3 routing methods. And the first RFC is on just general introduction to the problem of mobile ad hoc networks. There are 2 more RFCs which you don't have to read right now, not for this course, but if you need it, you can read them. And there are internet drafts, even more optional, this one drafts which are available.